Well, actually, it's a privilege and an honor to be here. Thanks a lot for inviting me and taking a risk on me. I hope I live up to your expectations. So, uh-oh, where'd it go? Okay. Is it working? So, as Mark mentioned, I'm actually with Amazon AI, specifically in AWS, and I'm also a professor at George Washington University on a leave of absence currently. So what am I going to talk about today? Low resource scenarios. They pose for us challenges as well as opportunities, I believe. And I hope I'll convince you that this is the case by the end of the talk, so you'll be like, all of you want to work on this kind of problem. So, oh, yeah, I don't know how to use the clicker. So it should be clicking. It's not clicking.
You have to take the right-hand side.
Oh, the right-hand side. Oh, okay. Okay, to go forward, okay. So data, also known as the gasoline of the 21st century. So almost 90% of data out there is unstructured. A new era of data is flooding us, right? But it's also a genuine treasure trove. So our basic mission is to make sense of it, right? At least this is my understanding. So the idea is that we want to convert data into valuable information. So data sciences, analytics, NLP with machine learning, this combination. Really, right now we're living in a situation of like a golden era, I believe, or maybe even a diamond era, where advances in algorithms, together with machine learning in particular, are creating this kind of juxtaposition of opportunity that is really very nice to see. But also, it's coupled with hardware advances, which is really, really cool. So we start doing things at scale, on a large scale, in very, very tractable ways. So, you know, we're living in a hallelujah period. However, in the world of unstructured data, many domains, genre, languages, dialects exist. So many languages in the world without sufficient resources. So we have lack of automated resources, automated data. Even if a lot of data, there is a big lack of processing tools. So there is this ubiquity of low resource scenarios. Idea our desiderata, in a world of this globalized communication, we'd like to have universal solutions, but also with a local flavor. So there is a need for processing all kinds of languages. Applications need like IR, IE, information extraction, machine translation, dialogue systems, automatic speech recognition, text-to-speech, bias detection, fake news identification, and beyond. So all of these technologies need data and need data to be processed in interesting ways. And essentially, we want to be catering to online customers in their native language, and also affording them access to information, to the available information in other languages. So this notion of a global citizen really permeates a lot of our thinking. I don't think it needs any more convincing, right? So let's move on. So one approach to how to handle this is to devise solutions for each and every language out there. But that begs the question, what is a language, right? So is it a political construct? Is it some kind of differentiator? Who knows? But anyway, it's constrained by dialect, register, style, genre, domain, and you name it. There are multiple dimensions, right? And we need lots of annotated data per language, variants. So depending on who's doing the classification, who's doing the categorization, we have all these dimensions that we need to cater to. When I go like this, you can't hear me, right? Oh, you can hear me? Oh, okay, cool. Okay. So too many varieties, but too expensive an approach. So what do we do? What are alternatives? So I'm going to try to convince you that there are alternatives, and these alternatives actually work. So there's a generalized agnostic fragmentation approaches, which exploit character and sort of like subword level representations or feature engineering and so on and so forth. But there are also the Robin Hood approaches, which is basically leveraging the rich to help the poor. So we have approaches that are, you can exploit aligned, bilingual, multilingual resources, such as parallel corpora, dictionaries, knowledge bases, like structured data. You have approaches that exploit linguistic affinities, such as language family relationships, language similarities. You have approaches that actually even exploit unrelated, and these are the kamikaze kind of people, right? So you look at comparable corpora, unrelated corpora, and then you go like, huh? But it works, so, or at least to some extent. So I'm going to talk a little bit about each one of these, just a tad, in today's talk. So In the first category of these generalized solutions, we looked at the problem of language identification. We looked at it in two different scenarios, where you have it on the level of a token meaning a word in a sentence, and on the level of sentences. So on the token level, which is typically referred to as linguistic code switching, you're trying to identify what language is each token pertaining to. So let me just show you an example, just a visual. So this is a code switching text that we get from Arabic. The red stuff is in standard Arabic. The black stuff is in, the black stuff is in modern standard Arabic. And that's the standard that's spoken, that's actually the language of education in the Arab world. But what's actually interesting about this, you think, well, that's straightforward. I can identify the red stuff versus the black stuff. But actually, what makes things more complicated, that there is this blue stuff. This blue stuff here, there are things that look like modern standard Arabic, but they actually are dialectal Arabic. And they are sort of like, hiding. They're disguising. So the solution to this problem is to do language identification on the token level. And it's a very challenging problem. So we devised lots of approaches, but I'm going to talk about two simple approaches that we did, which actually beat our state-of-the-art approach, which was kind of a bummer, because it was like really such a simple model. So we called it Lily. And the assumption is that each language has its own character pattern behaviors and combinations relating to its underlying phonology, phonetics, and morphology. The ideal solution is that there will be some kind of an impossible list that's created, that you know that this sequence of characters should never occur in this language. And therefore you would learn, you just use them by fiat, and you use them as a pattern, and you just have it work for you. But it's really very hard to find such sets of sequences, so to speak, per language. So a practical solution is to do character level modeling. And these are pretty simple. So you're trying to maximize the probability of those things that you see in a language, and you're trying to minimize or mute the things that you don't see. And that's kind of, you're doing this in a soft constraint type of manner. So in a way, we're approximating this list that doesn't really exist prescriptively. So we looked at 6 language pairs. So we looked at English-Spanish, Nepali-English. So similar to what I showed you with the modern standard Arabic and dialectal Arabic, we have the same thing happening with Nepali and English, Spanish and English, modern standard Arabic and Egyptian. We have something called Arabisi English, which is basically Arabic written in Latin characters. And you have the flip side of this, which is Arabic Ngari, which we call Ngari, which is basically English written in Arabic script. And you have English Hindi. So obviously, if you have the encoding, you're right, that's not even a question I'm going to entertain, because the encoding gives it away, right? If it's like in Latin characters, or if it's in some kind of script that is different, then of course you can detect right away. But actually, I'm dealing with a situation where you're using exactly the same script for both languages, right? So I hope that's clear. So the idea is, So the idea is to leverage very simple features, and we trained a CRF model, which is also a very simplistic model, that classifies each token of a new input and a sentence into one of the 2 languages, language 1 or language 2, modern standard Arabic, Egyptian, English, Spanish, Hindi, English, and so on and so forth. And we also, for the language that had the most resources, we just had a word level model, like a very, very simple language model in English, or if English happens to be one of the languages, right, and it's a high resource one. Let me tell you about our performance. So the best published results to date were beaten across the board for all 6 language pairs, except for modern standard Arabic and Egyptian. And in fact, our best handcrafted model for Egyptian modern standard Arabic, which is called AIDA, is the state-of-the-art to date, and it's at 92.8 or 92.8 right now, 92.3 at the time of this publication. But the bottom line is, it came very, very close. So 90.15 came very, very close to 92% with doing nothing, really. It was just really such a bummer. And we had all kinds of features and all kinds of hand-engineered stuff and all the knowledge in the world, but with everybody native and what have you. So it was really a nice surprise. We got a publication out of it, which is a nice thing. But essentially we said, okay, what if we do absolutely nothing? Like we just throw everything at this classifier, all the languages put together, and try to identify the harder language, the minority language in this group. And we did that, and we were surprised that we got very competitive results as well. So it looks like this task seemed to be relatively, simplistic in a sense. So better than the published results, we got, if you look at the third column, I could start using this here. Look at the third column here. Look at the third column here. The results were even beating the best published results in this case, and comparable to our binary one, the Lily one. And actually, on Egyptian, it significantly outperformed the best published results. And even beyond that, it actually beat, as I said, our own numbers from the binary one that had a little bit more feature engineering going into it. So that was an interesting result. And we said, okay, so we have these models now on the token level. How do we do on the sentence level? So now you can imagine you have a document that has sentences that come from one language, followed by a sentence from another language. So you don't have the intrasentential code switching, but you have the sentential code switching, right? So you've got things happening, changing all over. So this was done for vardial, and the task was to look at languages that are close to each other. So you have here Spanish that comes from Argentina, Mexico, and Spain, Malay, Indonesian, French that comes from Canada versus France. And the task was to identify between these different dialects or different variants of the language. I wanted to see what kind of modeling could we approach with. So, and the second task was to do a distinction between different varieties of dialects that come from different parts of the Arab world. So this was a more challenging task than what we had before, but again, it's also coarser grained because we're looking at the sentence level. And in this case, we're looking at Egyptian, North African, Gulf, Levantine, and Modern Standard Arabic. We had two models, a feature engineering one, a logistic regression one, and a feature representation one, neural nets. And it was a very simplistic neural network, actually, with very few features that had character representations, as well as when we had, so there are two varieties of this task. One of them was an open task, one of them was a closed task. In the closed task, we're not allowed to use outside resources, and the open task, we're allowed to use outside resources. So in that case, we were able to use gazetteers and dictionaries and so on to give us a little bit of a hint toward where this data came from. And the idea there was that Twitter would have geolocation information, so we could use that kind of meta information as part of our modeling. So both tasks, we used character engrams and word level representations. And in the open track, we used lexical features that I just mentioned. So just to give you a sense, here in this closed class, in the task one, for these different varieties of Spanish and French and Arabic and Indo-Malay, the training data, so we had 3 test sets. One test set was in domain, so a high resource situation. And then you have 2 test sets that were low resource, out of domain. So they came from social media, right? In terms of our performance, so our best results came from logistic regression, actually, not from the neural net. But we did not invest much in the neural net at that stage. We just did something very simplistic. But we ranked #1 for out-of-domain scenarios, just using these word and character level representations and using some of these open features that I had just mentioned. In task 2, we did a little bit of pre-processing just to normalize some of these character variants. And as I said, we used some dictionaries for the open task. And just using little things because there was Twitter data that we had, and the Twitter data had some markers indicating geolocation. So if it came from Kuwait, we know that this is Gulf Arabic. If it came from Tunisia, we know this is North African Arabic, for example. And again, we used logistic regression, and we used a a neural net system. And we, in the open class, we ranked #2, which was really surprising again, because we did this literally in a week. And in the closed one, we ranked #5 out of, I think it was 10. I think some of the organizers might be here actually from this task. But I think it was out of 10 systems. But essentially, the overarching conclusion is that these character models combined with very simplistic word features work very well for this task of language identification, whether it's on the token level or on the word level. So that's the take-home message. So let's move on to Robin Hood style. So how could we leverage the rich to help the poor? So I'm going to talk a little bit about exploiting aligned systems, aligned resources for different tasks. So I've worked on this forever. It's like I've been working on this for the past, since my grad. Actually, I did my PhD thesis on word census ambiguation in this setting of like low resources. So I've worked on word census ambiguation, inducing senses over cross-lingual word alignments, semantic role labeling for low resource scenarios, again exploiting cross-lingual resources, sorry. Automatic resource creation, so how do we induce dictionaries, bilingual, trilingual, multilingual dictionaries. We also looked at cross-lingual sentence mappings, so looking at neural sentence encoding models, and how do we do this in a way that relies on parallel data, and you start relaxing that constraint of parallel to comparable to unrelated. I'm going to talk a little bit now about specifically the second one, because that's one of our latest work that just came out in IWCS 2019, which is semantic role labeling for low resource languages. So as I said, we have a myriad of languages. There are over 70,000 living languages in the world. And there are very, very few semantically annotated corpora. If you think of the proportion, it's less than 0.0001% of the data that's out there for the languages that is annotated. So there's a considerable effort to develop semantic role labeled data for all kinds of tasks. So, I think I missed that slide. So essentially, for those of you who don't know what semantic role labeling is actually where you identify a predicate like eat. So let's say open. John opened the door. So John would be the agent who actually opened the door, and the door would be the theme that's been acted upon, that has been opened. And there are several frameworks, several ways of expressing this. And why is that relevant? Why do you want to identify who's the agent versus who's the theme in a relationship where open would be the predicate? You want to know this information so that when you're doing, for example, question answering, you want to know who did what to whom. Where did the answering questions like the where and the why and the how, they're all related to these semantic roles. So semantic role labeling is one of our enabling technologies that people build in order to be able to grasp this kind of information and use it for relation extraction, for question answering, and so on and so forth. So I should have had a slide about this. Sorry about this. So taking a look at this example. So you have here the word congratulate, and it's related to I congratulate him. So this is an A0, meaning the agent, him being the patient, whatever has been acted upon. So there is a relationship that's happening here, and then there's an adverbial relationship that's going on between congratulate, which is the predicate, and on. But essentially, this corresponds to the sentence, I believe this is German. I don't speak German, but my student does, so she created the slide. So this would be a corresponding predicate here. And then what you want to get out of this is that ich and ihn are the A0 and A1 in this relationship, right? So we're going to play a bit of pretend here that German doesn't have resources whatsoever. So but of course German does have some resources. But think about Hausa and think about Tagalog. So just project onto those spaces. But essentially, we're trying to induce semantic role labelers from knowing something about English and projecting it onto another language, right? So, So basically, there are challenges for this semantic role labeling task. Basically, if you want to do this kind of projection, there's a lack of unified resources or annotation schemes for SRL across different languages. So that's the number one challenge. And people are working on this, but it's something that people need to invest more time in. There are also previous studies that basically make the assumption, even when you do this projection, you need to have a lot of tooling that happens on the target side. So say you're projecting from English to Tagalog, you'd expect to have processing tools for Tagalog, meaning part-of-speech taggers, lemmatizers, which in our book, people who are NLP practitioners, these are so simple, right? But actually they're not, especially when you start going to languages that are very different from English. We make a lot of assumptions. So I've worked on Arabic for the longest time, especially on Arabic dialects. Building a tokenizer for Arabic dialects is still an unsolved problem, which is kind of interesting, even after 15 years of working on this. But essentially, the assumption is that we have these tools available in a supervised fashion that we could actually leverage for these different languages. And a case in point, looking at semantic role labeling systems that don't have very accurate parsers, for example, syntactic parsers, perform dismally, actually. So on languages like Arabic and Hindi, because we don't have really good quality parsers for that. So it's not really realistic to make that assumption that low resource languages would have these tools. So that's kind of our motivating point. So I want to go from completely raw text on the target side to complete SRLs. Is that doable? Is that achievable? So that's a typical low resource scenario. So, and we want to do this in a certain framework that leverages dependencies. And the assumption is, the only assumption we're making is that you have some kind of parallel data available. And that's not a very far-fetched assumption to do across languages. So let me just throw it out there. Things like the Bible, the Quran, they exist in all the languages that you could think about, right? Because of people investing in these translations. But are they the kind of genre or domain or style that you want to be leveraging? That's a different question. But at least you have something, right? So our objective is to build a simple and yet robust semantic role labeling system for these situations or these frameworks, these scenarios where you don't have resources whatsoever. So what is our model? We build a model that only relies on raw text in the target language. It's inspired by the work of Marchigiani et al. Of 2017. But we did some variations on that in terms of the model architecture and in terms of also the kinds of resources needed. So this model, what I'm called M17, relies on almost gold part-of-speech tags and lemma information that you get. And lemmatization is a very challenging problem, actually, especially if you start looking at morphologically rich languages like German, Russian, Czech. It's not that straightforward, right? So they make that assumption. So in our case, we said, we're not going to go with that. We're going to completely go away from that situation and work with characters, and that will be it, character representations. But we're going to play a lot with the model. So the experiments that we had is that we looked at source language being English, and we wanted the target languages to be German, Spanish, Finnish, French, Italian, Portuguese, and Chinese. And the reason we looked at these languages is that we had a unified platform that had these annotations, semantic role label annotations, across these languages, from English to these other languages. And we looked at parallel corpora that were available. So there were parallel. Why does this thing move alone? It's moving on its own. Oh no. Okay. So you get a look ahead. Okay. Europarl and multi-UN are also parallel corpora that we have. So, and we looked at ways of getting word alignments on the token level, and these exist like FastAlign, Giza++, and so on. In this work, actually, we used FastAlign. I don't know why I have Giza++ in there. It's actually FastAlign that we used. And essentially, just to give you a hint of what this universal prop bank looks like, the one that has this unified framework for annotating data, it's actually maps different predicates from all the languages to their right exact sense in the other language. So a sense like run a store is different from run a machine, run a marathon, and it's different from run a company. So they would have different senses with their different argument structure, and they map to each other. So what did we do in our projection experiments? So you have the source language, in this case English, and you have the target language, and this is a parallel corpus. You identify the predicate. First thing that you need to do is to actually build a supervised SRL system for your English language, right? So because your data is not necessarily going to be data that comes with that information. So what we did was we actually emulated the system, the M17 system that I told you about, which uses word embeddings, pre-trained word embeddings, and we also used part-of-speech embeddings. We used character representations and deep BiLSTM encoders for the final representation of the predicates. And we also made the predictions are made by performing an affine transformation on the BiLSTM output. So once you have that supervised SRL system, so it's basically, this is syntax agnostic. So it doesn't take syntactic features into consideration, but it heavily relies on part-of-speech tags and lemma features. And essentially what we do is that we start doing annotations, we start doing projections across the parallel corpus on the token level to the words on the target side. So we project, for example, the predicate, the agent, the theme, whatever it is, the roles that we have that we've devised from the source side to the target side. And we filter out only clean alignments. So we care about only clean alignments. And the definition of clean is constrained by density. So we look at the density of the alignments and so on. And we had a threshold that we arrived at empirically. Once you have the projected SRL data, you start having a C model, what we call a character model, which is a very, very basic model. So I only have representations of character embeddings. But what we did there was that we extended the character embeddings from being a 2-layer bi-LSTM model into having a 4-layer bi-LSTM model. And it was quite effective, actually. And we had another variation on this where we said, you know what if we were able to employ an unsupervised morphological analyzer to use as a way of getting features, like, morphological features onto our model. And let's test with that, because that's not a very far-fetched assumption. So it's not assuming that you have anything tailored to this language, but you'd rather, it's sort of like discovering these morphological segmentations automatically. And we use Morfessor, essentially, which is basically one of the standard unsupervised morphological analyzers out there. And just to show you the results, so using the bootstrap method, this is our method from 2017, which basically does projections over alignments using some kind of clustering. It's essentially looking at a special cost function to prune noisy productions. But it used essentially very rich resources and very rich tools to make this identification. And the results are up there. We use that as our baseline. So for example, for German as a target language, our performance there was around 59.8%. For French, it was 71%. For Chinese, it was 50.3%. So these numbers are really bad. But there were the state-of-the-art unsupervised SRL numbers to date. Oops the daisy. Yeah. And our ceiling here is a supervised system that's trained on data that's in domain with all the right features, with like the full-fledged, full 9 yards kind of thing. So I wanted to see how far can we get, how far are we from the ceiling, so to speak. So we have 3 models. We have the SLM. SLM is basically when you use our model, but we added features from a supervised lemmatizer. So we said, you know what, we're not going to use part-of-speech taggers, but we're just going to use a lemmatizer in there. If we have, we identify the predicates and their lemmas, how far can we get? But we're not using POS. And USTEM is basically using Morfessor, this unsupervised morphological analyzer, for giving us the same features, but this is obviously more noisy. And it's more noisy because it comes from an unsupervised framework, right? And then our C model, our C model, which has no explicit POS nor lemma information, whether it comes from supervised or unsupervised, is really the very impoverished poor solution, so to speak. But the bottom line is, in this, okay, I'm getting really, sorry, I'm using this in the wrong way. I just wanted to highlight that all 3 models beat the baseline, and actually the results coming from the C model, which is our impoverished model, are actually comparable to the results that we got from using linguistic features, whether it's using supervised lemmatizers or unsupervised lemmatizers. So that was really nice to see that kind of thing happening, which means that you actually can bootstrap from completely raw text all the way up to SRLs. We don't beat state-of-the-art when it comes to supervised systems, but we're beating at least our comparable sort of like brethren. So, okay. And we also wanted to get another data point on this. We wanted to see how well does our model do in a supervised setting. So if you don't have any features, like our model architecture with the bi-LSTMs, the deep character representations, how well do we do? And actually, if you look here on this slide, with the supervised lemmas, our results are actually beating state-of-the-art for English. They are a little bit lower than German. They're beating state-of-the-art for Spanish, and they're beating state-of-the-art for Czech and for Chinese. And actually, our very, very poor one, the one that's called C model in the previous slide, is actually also comparable to that and even beats within the context of Chinese. So what are the observations here? Careful modeling together with deep networks and on the character level seems sufficient for encoding semantic meaning when coupled especially with joint modeling of arguments and predicates. So I'm going to go quickly over the next couple of things, but I mean, I'm expecting people to ask me questions, so I'm going to be able to delve deeper later on. So how do we exploit linguistic affinities? So that's an alternative approach. So right now I was just talking about looking at bilingual resources and projections. But now what I want to talk to you a little bit about is exploiting affinities between languages. So if you know something about the languages that you're trying to treat, and you know that they're related somehow, how can you exploit that? So we have this posited in the context of machine translation, a machine translation scenario. So basically our objective is to enhance cross-language variant statistical machine translation in the absence of in-domain data, so in the absence of relevant data. So, so those of you who are familiar with how machine translation works, you're typically relying on parallel data between, say, English and Arabic, and you want to have data that's correspondent. So a lot of people leverage the Bible, they leverage the UN data, and so on, to build machine translation systems. But basically, in our scenario here, we want to leverage Modern Standard Arabic because our target is to do translation from a dialect to English. But we don't have anything in the dialect. We don't have parallel data at all in the dialect. So how do we go about doing that? So it's a completely poor person's solution. So we looked at the problem of false friends or faux amis. And just for those of you who don't know what that is, so essentially they're things that, that mean the same thing. Sorry, they have different meanings, but they look alike. So they are like things like the last row down there, which says gift and gift. So they have similar spelling and they have different meanings. And also you have the same thing happening with library and librairie, the French word. And they have similar, they don't have similar spelling, but they're still a false friend. So just to give you a sense of how this works, you have a situation like Modern Standard Arabic together with Egyptian, which is a dialect. And you have a word like zy. 5 minutes? Seriously? Okay. Time just flies. Essentially, the idea here is to say something like uniform and clothing would be the word in Modern Standard Arabic. But in Egyptian Arabic, the same exact word, the same homograph, which looks exactly the same, has two meanings. It has the meaning of such as and like, and it also has the meaning of uniform or clothing. So, but it's the less frequent one. So this is the problem. The majority one is the one that is the one on top. The one in the bottom is the one that's actually equivalent to the Modern Standard Arabic. So what's the idea here? So I'm going to run through this. So the idea is that you don't have enough parallel data from the dialect to the English, but you have a very robust system in the standard to English. So what you want to do is replace those words that look like Arabic, like Modern Standard Arabic, by things that are more equivalent. So a word like MVL in that spelling, it actually means in Modern Standard Arabic the same meaning of the more dominant sense of the word ZY in the dialect. So if you are able to figure those out and replace them by the appropriate replacements, then you might improve your machine translation system. So I'm going to click, 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 click. So essentially what we did is that we identified these false friends automatically, and we did an extrinsic evaluation of the quality of these false friend identification and replacement in a machine translation scenario. And just to give you I see I had a lot of slides. So we did a lot of tricks using clustering and sense induction and all kinds of fun stuff. And essentially, we are, after all that work, we're able to beat our baselines, which is lovely. And we came up with we were at 20.7 versus 20.1, which is on the blue score. It's a really horrible number, but you know what? We're the best out there. So, so that's what counts. But then, our best system with all the tricks and everything was able to only get us very close to the baseline, which has no replacement whatsoever, where you don't do any identification. But, of course, you would not leave it at that. And by the way, this got a Best Paper award. So I just want to say that. We actually went in and did a qualitative analysis of the results. And this is where we did a really good job. So essentially, we're able to get the exact right translations to a larger degree. So just to take a look at this, I'll just give one example. So you have here, this is the replacement translation. Let us leave our differences and unify. The baseline translation, we disagree and suffering from. So ours reads a little bit better, I hope. And we were able to do this, but Bleu does not capture this. The metric that we're using does not capture these nuances. which is kind of a shame. But of course, we had to beat through it, and we showed them that it works. So the last thing I'm going to talk about here, 2 minutes. So my thing says 7 minutes. My tracker says 7 minutes, but anyway. So, but anyway, I believe you though. Yeah. So, so our work on exploiting comparable and unrelated resources. So we've worked on unsupervised induction of cross-lingual word mappings. We've worked on learning how to transfer for emotion systems that actually work on emotion classification and identification. And we also worked on automatic resource creation and augmentation. So you know what? I'm not going to go into this. I'm just going to click, 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 just to show you. So our approach, which was published in Tackle 2018, was essentially looking at unsupervised initialization of word mapping. So people have done this by mapping between corpora, between words and corpora cross-linguistically, by assuming that you have some kind of seeding that comes from a parallel resource, like you have a bilingual dictionary that bootstraps the whole process. And we know that these methods where you're trying to discover the relationship between pairs of words across languages. So the assumption is words like house and garden are closer to each other. They have the same distance if you think about house and garden in German and house and garden in Arabic and house and garden in French and so on and so forth. So you exploit the relationship, the proximity of these words to each other, and you say these pairs of words are going to have the same relationship when you go in other languages. So that's kind of the basic assumption. And based on that, you start bootstrapping from that process, and you do some kind of greedy search and optimizations and so on to discover word mappings. And in our work, we said, you know what, we're not going to start from a supervised initialization. We're going to start from spectral embeddings in a completely unsupervised approach. And this work resulted in the following. So just to give you a sense, where did it go? So yeah, so just to give you a sense here, so this top graph, so this graph here, shows you if you start from our approach with spectral embeddings versus starting from a supervised mappings from the get-go, we are very, very close, especially when you do the evaluation using parallel corpora. If you do it on comparable corpora, we're pretty close as well. If you do it with completely unrelated corpora that were designed to be completely unrelated, out of style, out of domain, out of genre, we're again very close to the bilingual, supervised approach. And here, the baseline that we have here is if you start from some random initialization. And we showed this that it works for Arabic English and also works for French English. So just to give you a sense of the things that we got. So you see here negotiation, for example. After, in the final steps, we get dialogue, argumentation, dialogue, consensus. And so the words seem to be really, really good at this stage. So what did I learn over the 20 years? Fast forward. So basically, I cry a lot. And, but basically, the evidence seems to suggest that there is some core semantic space that exists across languages, some form of an interlingua, but with a modern twist. That's kind of the idea. And we want to discover this in a hybrid manner. So we're looking at data-driven approaches throughout my research agenda. We incorporate different levels of explicit linguistic knowledge for both feature engineering and feature representation, and especially helps a lot with these low-resource scenarios. So I just want to acknowledge that this is funded by a lot of people and with a lot of collaborators. So I thank them. But I wanted to delve into this for like 2 minutes. So what I do at Amazon, so that people might be curious and how this actually translates into the work that I'm doing there. So I work on a lot of HLT technologies within AWS AI. I look at information extraction, but I'm also the lead on dialogue systems conversational AI within the context of Amazon. And these are kind of the technologies that are out there for us. So we have machine translation, we have information extraction, like sentiment analysis, name entity recognition, summarization, so on and so forth. We also have text-to-speech. We have recognition, which is image processing. And basically, the part that I'm interested in, or that I'm currently focusing on, is this Lex. It's a fully managed AWS service which builds conversational user interfaces, but it caters to enterprise-level customers. So it's very different from Alexa. So you can think about it as sort of like the core of Alexa. Like you see there, I have the two A's separated out. And it's multimodal, so it works with text and speech simultaneously. And it actually targets goal-oriented chatbots. So it's basically you engage with it for services like I want to order a pizza, I want to order a drink, and so on. And it caters, we don't cater to like first-person customers. But I just want to say one more thing about this. How does this relate to the low-resource scenarios that we have? So basically, I just want to say that the bot developer provides us with sort of like a core bot definition of what the intents are. So if he wants to order pizza, and the kinds of toppings on a pizza are provided at the initial development time, they give us maybe, I would say, 100 data points, and we're supposed to build the chatbot on the fly in under a minute. So when I first joined Amazon, I looked at my boss and I was like, are you crazy? That doesn't happen. It doesn't work. And, but basically it does. So, so we're able to build those. But imagine this is the ultimate low resource scenario where you don't have training data whatsoever. So what do? Do you use BERT? Do you use Elmo? Do you use these transfer learning approaches? Of course, we looked at those. The problem is the time. As I said, the SLA is to build everything under a minute. So this is a very, very big challenge, and this is what we're working on right now. So we do a lot of data augmentation, we do a lot of smart data selection, we do a lot of smart algorithmic, and pay attention to a lot of attention. So, but anyway, the bottom line is this is kind of the challenge that we're facing, but it creates a great opportunity because we're literally sifting through algorithms, through models, and so on and so forth. So I'm going to stop now. And I just want to say oh gosh, I had a lot of slides. So, oops, no. I don't know what's going on, but anyway. So I just wanted to highlight that we have, well, thank you very much, but I wanted to highlight that we have different ways of engaging with us, and we're actually hiring. So I wanted to put a plug in for Amazon. And we could engage with people through actual hires or through internships. We also give faculty awards, we give research awards. We have Amazon scholars who are sort of like part-time employees within Amazon. So we've thought about lots of programs to engage with academia and with even small industries. So, so reach out if you're interested. Anyway, thank you very much for listening, and sorry for the rush.
Thank you, Mona. Oh, this is pretty awesome. Better now, yeah. So, thank you. I think I know the next speaker, so we still have some time for questions.
Okay.
So, do you have questions? Yeah.
So you spoke about there being this sort of latent language, a generic language, and how do you see sort of us learning that, and what's sort of your approach to learn this sort of language of all languages, sort of implicit, parametric, whatever language model that's hidden behind all language?
So I actually don't think there's a specific language, but I think there is a specific way to map from one language to the other. And different languages have different ways of mapping to each other. So, if you're mapping from, so we looked at this in the context of emotion detection. And we were looking at a language like Uyghur, and that has no resources. So what we did, we know something about language families. So we ended up getting things from Arabic, Russian, Chinese, and Turkish, and we put them together. And we were able to leverage that together with a very small seed of something like a dictionary from Uyghur, and we were able to bootstrap an emotion detection system for that. So knowing something about the languages, knowing how they pattern with other languages. So for example, we know they share lexical items with one language. They share syntactic structure with another. They share morphology with a third. You leverage these types of components, and then you start engineering your modeling to reflect these different dimensions. So you take the linguistic knowledge that you have and you try to sort of translate it into models and architectures that could actually be leveraged. But I don't think there's a specific, like language that's universal, so to speak. I think you have, I come from a school, I come from the Chomskyan school where you have like the parameters. So you just turn on parameters, turn them off, and so on. Yeah, so yeah, that's kind of what I say. Yeah.
So this is less of a question, more of a comment, really. I'm a trained linguist, and I can sympathise with your difficulty of having to analyse typologically very different languages, and if we have time, which we obviously don't have, I would be interested in the syntax model that you use, and you just mentioned you work with Chomsky's theories, and I have a hunch that there are quite a few languages where Chomsky's model would break down and have to work with something different.
I couldn't hear. Could you say that last part? Yeah. Now I could hear you. Could you just repeat that last part?
I suspect that there are quite a few languages, especially the smaller ones, minority languages, where Chomsky's model would break down, and you would have to come up with something entirely different. And I would be interested in hearing more about that, but just if we have time.
So we're not wedded to any syntactic formalism per se. So a lot of our approaches are data-driven, and we work mostly with dependency parsers because they're the closest thing to semantics. That's basically the overarching theme of the research happening in my lab. But we also care a lot about models that could preserve something about syntactic structure. So our latest work at NACL 2019, which I did not go through here, was actually looking at how do you do neural sentence encoders that actually preserve syntactic structure when you go cross-linguistically. So how can you preserve that information? It's kind of like a poor person's solution to doing explicit syntactic modeling. But we looked at how these models are able to capture these relationships through doing windows of bigger sizes and so on and so forth. So, and we looked at different languages that have different characterizations. So free word order versus morphologically rich, profiles, so to speak. And it seems to be working well. So it's more like we're trying to discover some of these things, and we're sort of inspired by the linguistic theories out there. So when I said I'm Chomsky, it's like I went to Maryland, which is like very heavy duty Chomsky. So that's what I meant by inspiration from that perspective.
Have you, by any chance, ever worked with Roland reference grammar?
Yes, we have at some point, yes. Yeah. So we looked at different formalisms actually, but tag grammars and CCGs and variations.
I think we take one last question.
Actually, it's not necessarily from me, but I've heard this asked. Someone from maybe a Swiss guy workshop yesterday had asked, maybe the linguistic situation in Switzerland is kind of like the situation there in Egypt or in the Arabic-speaking world.
Right.
How can we, or what kind of wisdom could you perhaps give us in working with Swiss German? How to start, how to proceed about it, and what kind of tricks do you think that we can leverage and what we can?
Mm-hmm. So we've looked at this problem a lot. So within the context of Arabic, and obviously in the work that we did for code switching. So we actually run a workshop every couple of years on computational approaches to linguistic code switching. We're interested more in the code switching that happens on the interstitial level. And I don't know if this happens in Swiss German. So do you mix German and French or Romansh in the same utterance? Or is it just across?
That's not the case of Swiss German. I mean, Swiss German is a strong dialect of German.
Swiss, yeah.
And you can consider it as a different language, basically.
But do you mix different codes in the same utterance? Or do you just speak Swiss German?
Only if you have proper nouns.
Yeah. Well, I mean,
SMS messages where there are a lot of things.
Right.
What totally would expect.
Yeah, it's interesting because I think with social media, people are starting to come up with the realization that people code switch. If you're bilingual, you naturally code switch. That's, I mean, unless you're very strict about it. Most children growing up in a bilingual environment or multilingual environment, they tend to code switch intersententionally. So back to your question. Creating resources and annotation standards, I think, are crucial in order for you to get anywhere. And we've done that for Arabic, we've done that for Spanish English, we've done that for Hindi English. So maybe we should talk about collaborations because we already have some guidelines of how to create annotations, how to unify them, how to do this on crowdsourcing platforms. So this is another hat of mine that we've been looking at this problem. But Swiss German, so I know about Yves' work on Swiss German when he was visiting with us at Columbia. But I'm for the intersentential cases, so it seems to me to be a much easier problem. The intersentential one is really the challenge if you have that, especially if you're looking at social media and so on.
But what can we do with the code-switching bit?
What could you do?
What can we do with the code-switching bit?
What could you do with it? So machine translation, speech recognition, all of these technologies just fail when you have code switch data. They just fail. So what we do is that we do all kinds of domain adaptation. So things like the borrowing from language affinities, that's one of the solutions that we have. We've played with domain adaptation models, and we've played with, like you have different language models with different proportions, and you play with densities associated with them and how you do the modeling for them. So there are lots of approaches that we've looked into. Yeah, but there is a lot of work. If you look under code switching, for computational approaches to code switching, actually, there is several interesting works on that. And it's agnostic of the language pair or the languages involved. Yeah. So.
Okay, so thank you very much again.
Thanks so much for having me again.